thanks very much for inviting me to give this talk. It's something that is close to my heart. We've been working on pyrite for probably the last 15 years or so, mainly from the point of view of understanding the genesis of ore deposits, but it has the spin-off, of course, of having an application in mineral exploration, and that's what I'll focus this talk on. So we've got a team of people who've been working on pyrite with me for some time, as you can see there. Several PhD students. Leonard Daniszewski looks after our laser lab, and we now have 5 laser ICP-MS units running, and 2 of them are dedicated to sulphide work. So it all starts with the power of pyrite, the most common sulphide that we know, and is present in just about every ore system you can think of. So that's the real value of using pyrite. It's so easy to find. You don't have to look very far. Even in barren rocks you can find a bit of pyrite. It's not complex at all. Whether it's crystalline, as in the left there, or whether it's very fine framboids with overgrowths, as shown on the right, we can tackle it all with the laser system. So the unique quality of pyrite, as with other minerals we've been hearing about, is that it absorbs a lot of elements into our structure. And you can see there elements like nickel, cobalt, arsenic, gold, copper, etc. will go into the iron site, and into the sulphur site we'll get elements like selenium, tellurium and arsenic. Some of these elements don't actually go into the structure. They occur as micro-inclusions of sulphides or tellurides or other phases. We're not too worried about that. We don't get rid of the micro-inclusions. They're part of the story. We want to look at the whole of the pyrite chemistry. The laser system is similar to ones you've been hearing about. That's Sebastian Meffra, who does a lot of our work, putting in some samples into the sample holder there, and the laser comes down through that black tube. And we analyse commonly about 50 elements, including gold and platinum group elements. And the simplest way is to just do spot analyses, identify the pyrites, make a note about their texture. In this particular case, you've got early pyrites that are rounded, overgrown by euhedral pyrites, and you can see some examples of analyses there of gold, tungsten and arsenic. But as I said, we do 50 elements routinely. The other technique is laser mapping. We've been doing this for a long time now, and that's particularly useful for looking at the metal paragenesis in the pyrites. This is something that's more involved in research, or when you're doing a detailed study of an ore system. It's not needed in routine exploration necessarily, but you can see there that mapping would have taken about 2 hours on the laser, and you can see little inclusions of gold sitting in a pyrite grain there that you wouldn't normally pick up under the microscope. They're the red spots are the gold grains. The green is the background of gold. That's the invisible gold in the pyrite. And you can see how that relates to arsenic in that example, and also to cobalt. And you can see how the cobalt is a later rim around the arsenic and gold-bearing pyrite. So there's a lot of paragenesis you can get out of this. And you can also understand whether you should be doing your spots in the core of the pyrite or on the rim of the pyrite, because you'll get a different answer with those 2 locations, as you can see there. So how do we use this? Just some examples as a discriminator, exploring for orogenic gold and VHMS deposits. We sampled a lot of different material in the local core shed here, the GSWA core facility, just from many drill holes that have been drilled in the Yilgarn, and we also did an exchange of samples with UWA and built up a database of pyrite in the ore systems here in the Yilgarn for VHMS or orogenic gold. And a few simple diagrams just showing you the differences, nickel against cobalt here. The orogenic systems tending to have a little more nickel in their pyrite. compared with the VMS systems, which have a little more cobalt. But you can see there's a lot of overlap there. That's not really a discriminator. If you look at gold and arsenic, this is a classic diagram with that curved line being the saturation line for gold in pyrite. Analyses above that line mean that you've hit little gold grains. Analyses below that line mean you've got invisible gold in the pyrite. And you can see in that case that the data overlaps very well. It's not a discriminator, but you can see the orogenic blue dots go to quite high levels of arsenic and gold. That's really the ore grade systems that are in that arsenic gold association. One of the better discriminators between these two ore types is tin and tungsten. A bit of a surprise really, but there's a lot more tin in pyrite associated with VHMS systems and more tungsten in pyrite associated with orogenic systems. We looked at all these elements and developed a score for the pyrite from VHMS systems compared with a score for pyrite from orogenic, and you can see the function that involves different elements there for the two different scores, with most of the red dots being pyrite from VHMS systems. This is not in the ore necessarily, but around in the halo also, compared to the orogenic field. So once we developed that, we then used it to look at other examples of barren drill holes that have been drilled in various places to see how they fitted into those targets. I mean, these holes were drilled at particular targets, of course, and you can see in this one that the data fits in the VHMS field, most of it being in the distal to proximal area. So you know you're in the right district, but you're not close to the ore body yet. Here's another example that was drilling for orogenic gold, and you can see the pyrites are in the orogenic field, and again they're mainly in the proximal part of that diagram. Another example, which you don't see very often, where you've got data that is in both fields in the one drill hole. This was very interesting. This is an orogenic gold system, and it turned out when we mapped the pyrite that the pyrite zoned, and that is those pyrites below the line came from the core of the pyrite, and that was an early core that was overprinted then by the pyrite which is more euhedral, the orogenic pyrite, which has most of the gold in it. So you're seeing an early, what looks like a VHMS type pyrite being overprinted by a later orogenic system, with all the gold really being in that later orogenic part of the ore system. So there you'd say, yes, you're right in close to the target, or you've actually gone through the ore body in that particular case. If we move now to sedimentary ore systems using pyrite, and I'll focus here on sediment-hosted lead zinc, or SEDEX type systems, as opposed to sediment-hosted copper. And you might have drilled some material like this. You've got a black shale or a sedimentary rock with bands of pyrite in it. Now, is it significant? Indrani Mukherjee, in her PhD studies, recently studied a series of drill holes from the MacArthur Basin, and those holes were looking at shales at various distances from the HYC ore body. We studied pyrite in the ore body and pyrite at various distances away from the ore body in those three holes you can see there. And it was interesting that the chemistry actually of the material close to the ore bodies, the nickel and cobalt, decreased in the pyrite, but elements like zinc, lead, arsenic and thallium increased in the pyrite. And we put that together in discrimination diagrams, fertility diagram, showing there that the one on the left, the orangey yellow dots there from the ore deposit, the black dots in the background, they're just a whole database we have of sedimentary pyrite in black shales, and you can see how the dots, many of them are in the background, so they're not telling us any of them, but some of them, those green dots there, come from a drill hole which is closest to the MacArthur River deposit, indicating a trend towards that deposit, giving us some confidence that there may be lead zinc mineralisation in the district. And then on the right hand side, the vector diagram actually takes you through those drill holes progressively towards the deposit, the MacArthur River ore samples being on the right hand side in that particular case, with increasing zinc over nickel and increasing thallium over cobalt. In terms of future research, we're continuing on this program. We obviously need to increase the number of case studies on a variety of different ore types, and Codes is starting a 2-year research project to do this. We're focusing on stratiform sedimentary lead zinc and sediment-hosted copper. We've got 6 companies that are willing to join this project. We need about another 2 to get it off the ground. So any companies that you know of that might be interested, please tell them to contact me. We're also continuing our case studies on gold systems. These are fairly well advanced. We've got a number of case studies now, so we don't need to be doing more case studies as such. We're using this as a feed for service through our laboratories. Thanks very much.